Welcome everybody to our webinar today. I am Jill Browning and I will be your moderator for our presentation today. I can see that we've still got some people in the waiting room that are still in the process of logging on, so we're going to give it just about another 30 seconds to a minute or so to allow them to join us as well, and then we will get started. So I appreciate your patience and we'll get started here shortly. Welcome everybody to today's webinar. As I mentioned earlier, my name is Jill Browning and I'll be the moderator for today's webinar, Put Your Nutrient Removal System on Autopilot. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. First of all, hopefully you should be able to hear me speak at the moment, but I do want to mention that should you guys have any difficulties with your audio throughout the presentation today, there are two different ways to connect to the audio system. You can use either your computer or call in via a phone line, so feel free to switch back and forth between those two should you have any issues with that audio today. And then also, due to the large number of attendees that we do have on today's presentation, we have gone ahead and muted everybody's lines, but no worries on that. You can still interact with our speaker. And in terms of doing that, you can ask your questions via the questions panel at any time throughout the webinar today. And at the end of the presentation, we do have some time set aside for our speaker to answer those questions. So we will have that Q&A session at the end. So feel free to ask any questions that may come to mind, and we will try to get to as many of those questions as time allows. Today's webinar is one of many in our upcoming Veolia Water Tech Talks program. Specifically for the month of May, we are featuring digital transformation. We had one that was last week on optimize your wastewater treatment facility to maximize capacity and minimize costly expansions. So feel free to go back, check that one out on demand, or also register for our upcoming one on May 25th. Additionally, we have made available our collection of on-demand webinars that we've conducted over the last few years. So you can access more than 40 on-demand webinars over at www.veoliawatertech.com. So feel free to go over to the website, browse the various topics that we have, and register for any of those that may be of interest to you. One other housekeeping note that we have is a PDF participation certificate will be made available to you at the conclusion of the webinar today. So you should receive that within about 1 to 2 days after the webinar. And then finally, at the end of today's webinar, you'll receive a quick survey requesting your feedback. It should take no more than 20 to 30 seconds. And for those of you who do complete that survey, you'll be entered into a drawing for a chance to win a $25 Amazon gift card. So if you would be so kind as to fill that out for us, we do greatly appreciate that and value your feedback. Now, before we hop into the main part of our presentation today, if you're not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider. And we offer our clients a variety of different technologies, services, and projects. You can learn more about us over on our website, or feel free to reach out to us after the webinar today as well to learn a little bit more about our capabilities. And then also in terms of supporting our clients, we do that through a variety of different markets, variety of industrial markets, as well as municipal markets as well, to help support water and wastewater treatment needs. So with that, now I would like to introduce our speaker for today's presentation. Mark Drake has been a water professional for over 20 years. He obtained his BS in chemical engineering with an environmental emphasis from Iowa State University. Mark has been part of the Veolia team since 2010, where he currently serves as Service Programs Manager and Product Champion for the Hubgrade line of digital solutions. Mark is also very active in the North Carolina American Water Works Association and teaching several classes for treatment facility operator certification. So with that, I would like to now turn it over to Mark to talk a little bit more about our topic today.
Excuse me. Thank you very much, Jill, and thank you everybody for spending a little bit of your afternoon with me here today. Our agenda is going to be focused on the Hubgrade Performance Plant nutrient removal based core features. To kick things off, I'll do a very short review of some basic nutrient removal information. I won't belabor that very much, but we'll just briefly touch on nitrification, denitrification, and the necessary types of things that need to be in place to achieve those objectives. And then we'll start to zero in on important aspects of control and where that's gone over the years, from basic DO control to ammonia-based aeration control. And then we'll really get into the heart of what I'm here to share today, and that is the Hubgrade Performance Plant platform that really takes the control of your nutrient removal system to the next level. And specifically, I'm focusing on the DO and nitrogen feature of that platform. I have a couple of quick examples of some real-world success. These features themselves, the DO&N feature, this sort of advanced control, it isn't anything that's necessarily new. It's been around for quite some time, and we've been implementing it in numerous plants around the world. There's a few new twists and things to it that we'll talk about a little bit today, and then we'll wrap things up and hopefully get a couple good questions. So first thing we'll talk about are some nutrient removal basics. As Jill mentioned, I've been in the water industry for well over 20 years, and nutrient removal is really where I have always lived in the treatment industry. I spent the first many years of my career designing, starting up, and troubleshooting nutrient removal systems, not with Veolia, with a different supplier. Then spent a number of years on the consulting side of our industry, and then found my way here to Veolia. I was the biological product manager for some time, and then moved into a service and digital champion role. So nutrient removal is something that I have been deeply involved in for well over 20 years. I'm sure most of you on the meeting today are familiar with the core basics of nitrification and denitrification, and the need to establish aerobic and anoxic environments to achieve those different objectives. This little schematic just simply sort of walks through going from what you would see in the influent to your wastewater facility that's generally going to be in the form of ammonia, and it being treated to form nitrate through the nitrification process, requires oxygen, requires a long enough mean cell retention time. You grow ammonia oxidizing bacteria, nitrite oxidizing bacteria, and form the nitrate. From there, in an anoxic environment, you then can denitrify that nitrate that you formed, ultimately forming nitrogen gas. So there are lots of different ways to accomplish that type of process, those types of objectives. Very simple systems to pretty elaborate systems with lots of recycles and things. It really sort of depends on how low you need to go. Control in these types of processes doing nutrient removal have advanced pretty substantially over the years. It used to be that outside of having separate reactor zones, and controlling recycle rates, controlling your dissolved oxygen concentration was about all there was to it. You needed to make sure that your DO concentration in your aerobic zone had plenty, it was high enough to enable full nitrification, but then you also have to have some concern over potentially being too high, particularly during low loaded periods and you know, the first several years after a brand new facility might start up, where you might only be at 30% of the design load of the plant. So there have been a number of different types of DO probes out there to enable online monitoring that work very well. There's some minor nuances in how control loops are set up to control DO, but generally it's a very well understood, common technique used in just about every system out there that would be doing nutrient removal. Over many years now, we've seen a substantial advancement in ammonia-based aeration control being used in our nutrient removal systems. That offers some improvements in energy consumption, minimizing the amount of oxygen and trying to maintain DO concentration levels in your aerobic reactor that aren't really any higher than they need to be to ensure you are fully nitrifying. There are some concerns that you do have to pay attention to in terms of possible nitrite accumulation and impact on the overall condition of the biomass and settlability and things of that nature. If you are, you know, constantly running at a very, very low DO set point for very long periods of time. But you know, these systems have been done for many years, as I said. When coupled with other forms of control, such as automated mixed liquor concentration control or automated solids retention time control, they are very effective, operate very well. So that's just a quick summary of the history of what's out there and been used in our nutrient removal systems from a control standpoint. We're going to really dive into now the Hubgrade Performance Plant platform, and specifically the DO and nitrogen feature, and we'll see how we utilize that to bring about the next level of control and really put the system on autopilot. Now, first, just a quick background on Hubgrade Performance Plant and what that is. If you've seen prior presentations, you may have heard the term Aquavista. That was a former different brand name that the system went under. There's been some overall consolidation in our organization of some of our other digital services that were specific in certain markets to have a consistent brand for our digital services throughout our different markets that we serve. And so that name had transitioned then from Aquavista to Hubgrade. And what we're really doing is capitalizing on the ability to make real-time adjustments to PLC set points via some complex algorithms that are running on a computer and that take advantage of the latest in digital twin technology and modeling to go along with the PLC program that's in place that's actually running the plant, and taking these to a level that you just can't do with strictly PLC-based control that you can do a lot with. You can have a lot of if-then sort of statements and P&ID loops and everything. But in today's control environment, you can really fine-tune things a lot more with digital twin technology and automated set point adjustment that is coming out of algorithms that receive various inputs in real time from the treatment facility. There are many different features that are offered with this platform that deal with anaerobic processes, the collection systems that are operated out there to minimize CSO events and smooth out incoming flows to our wastewater treatment facilities, all the way through all the different types of unit operations you can think of at the treatment plant. Our focus here today is really on secondary treatment, nutrient removal, and on that DO and nitrogen removal. But you can see just in the realm of secondary treatment, there are many different features that are available that all really work together to fully optimize the treatment facility. The DO and nitrogen removal, that's sort of the real low-hanging fruit. That's our aeration systems are the largest power consumer. Our nutrient removal needs, our nitrogen, our phosphorus effluent requirements are very critical and becoming more stringent every day. So we're focusing here on the really main core feature with that DO and nitrogen removal. But all those other features would continue to enhance the control and really work together with the DO and nitrogen removal feature. As I said earlier, this isn't anything new. We've employed these various algorithms in many different facilities across the world, for very small plants to larger plants. There are facilities with 1 million and 2 million population equivalents running this, all the way down to 10,000, as well as some industrial facilities that are using the Hubgrade Performance Plant platform. It is delivered today through the cloud, hosted on Amazon Web Service. All of the best, latest, and greatest cybersecurity protocols and procedures are in place to ensure that treatment facility networks are all very well protected in the delivering of this system to a facility. So digging into the DO and nitrogen feature, one core general theme here to keep in mind is this is applicable really in any kind of secondary treatment facility that is doing operating with activated sludge. The features are also applicable to MBBR type systems as well. And they are, excuse me, applicable whether you have multi-stage systems, single-stage systems, multiple recycles, one recycle. The different features that you might employ on top of the DO&N feature would certainly get more complex. The more complex your system is to enable the highest level of optimization. But the core DO and nitrogen feature, if you have an aerated tank that has biomass in it, the feature can be applied and can be beneficial. It really functions in the most simplistic terms in two core areas. One is DO control. So anytime that you want an aerobic environment, you want to control the DO. So there's a specific algorithm and numerous settings that fine-tune that algorithm to control the DO. And then there is a phase control. And that is allowing your aeration tank to be fully anoxic or fully aerobic, depending on the conditions in the facility. All this is, again, controlled via the algorithms that are fine-tuned based on a number of different criteria. It is a multi-criteria, as it says, and the core criteria that feed into it are ammonia concentrations measured in the reactor, nitrate concentrations as measured in the reactor, and of course, DO. Measurement of the different criteria is, of course, a very important factor in the success of any of these kind of systems, and is critical to reliable modeling and predictions, which are used in a variety of ways in the system, including things such as knowing when you have whatever tendency you have to overshoot. As we all know, when you make a change in any particular parameter in a treatment system, the impact isn't fully felt immediately. There is some amount of time. That's where the digital twin comes in, and you can anticipate when it's going, how long it's going to take to fully affect the change, and make your changes in accordance with that. So it is important that the signals be reliable and be accurate. So the type of instrumentation used to monitor ammonia, to monitor nitrate, does need to be suitable for the specific purpose that we're looking at here. That is where the system is set up with an automated data quality checks. So another advantage of having a digital twin where you establish a long history, and you can see how different conditions produce certain variables and how these variables change over time. You can predict pretty well if the reading that you're getting from a particular probe or analyzer is not where it should be. There are very robust data quality checks so that the system will know if a reading is drifting, if a probe is getting too far out of calibration, and the system will respond accordingly automatically without the operator needing to say, turn off this part of the feature because that reading is suspect and I don't want it to steer my plant awry or steer it down the wrong path. That is all optimized, all accommodated automatically by the system with that online data quality control. The operator is notified when any such instance is noticed by the system, but it will automatically have multiple fallback positions to enable the system to be as optimized as possible based on all of the information that it has available to it that is suitable and regarded as quality data to be used in the algorithms that are controlling and determining the new set points. The ultimate system, as I said, is using both ammonia and nitrate to determine the reactor state and to determine where the DO set point wants to be during any aerobic reactor state. But if the nitrate reading is suspect, the system is smart and won't use the nitrate value and will have an altered algorithm that functions based on just ammonia. If that ammonia is suspect, it will not use that, but it will use its most recent and historical cycling and the values that it has seen to control the system. If that is not considered to be quality data, then it will fall back and it will utilize oxygen uptake rate information that it has from the DO readings that it's had over time. It will fall back from there to average percent nitrification or aerobic time and how long those cycles are. So there's a series of algorithms that will make the best utilization of the information that is considered quality at that time and utilize that to optimize the system. At the end of the day, if all of the inputs of those algorithms are determined that they are not of a sufficient quality, then the system will be operating based on whatever default set points the operation staff has set in the PLC. Those are maintained, they're there, they're stored, and it will utilize those settings and keep operating. So regardless of what data might not be at a quality level that is usable by the system, it will still keep things optimized as best as it can. So on this slide, we're really looking at kind of two sort of extremes to sort of in a very simplistic way define, what is happening. On one end of the spectrum, you could have a very low load or very, active biomass condition where you have very low ammonia concentration in the reactor, and correspondingly high nitrate in the reactor. The system, if that's the type of condition you're in, it's going to be consistently working to reduce the DO set points, to reduce the actual amount of aeration or the amount of aerobic time, and it will prioritize denitrification in the system and run the system without aeration at all as much as possible, and ultimately stay between that extreme and then the other extreme, which you would see if you have a very high loading coming in, and you have a lot, you're measuring more and more ammonia in your reactor. The DO algorithm is going to be increasing the DO set point. The total amount of aeration or aerobic time is going to be increasing, and you will of course see, under those conditions, you're going to see increased BOD removal rate, you're going to see accelerated nitrification rate, and ultimately these two extremes are set based on, first and foremost, always ensuring compliance. So if you have an effluent total nitrogen permit value and you have an effluent ammonia value that you have to meet in your permit, the system will ensure that you're staying underneath those values. And then it's always working to keep things optimized and balanced to as great a degree as possible, given your current actual settings or current actual conditions, I should say, and stay in between those extremes. So a key aspect of that is tuning of the algorithms and defining for the phase control, aerobic and anoxic phasing in the reactor, how the system on those two ends, what essentially sort of setting the boundary conditions, how those will function. So these settings ultimately are used to tune the algorithms, and the measured ammonia and nitrate concentrations will then be used by the algorithm, and along with these tuning settings, to identify, okay, do I want to be right now in an aerobic state or in an anoxic state, and do I want to be moving toward more aerobic in the future or more anoxic in the future? Another core aspect of this also that is important that we do recognize, and that has to be recognized in any of these types of systems, are any mechanical realities of the aeration system. The ability to turn the air completely on, completely off, depending on the type of aeration system, there can be time limitations to that. So it is important, whenever we're going into an opportunity, to understand those realities and the overall setup of the system would build that into the algorithm and keep that in mind, so that mechanically the aeration system doesn't get into trouble by trying to start and stop blowers, way too often, and that kind of thing. So this is just one example of tuning settings related to ammonia and nitrate. There are a separate set of tuning criteria associated with DO as well, and that separate algorithm that's part of the system. So you have this set of algorithms that are keeping the system in balance between your boundary conditions, and in doing so, you're really driving the energy consumption to new lows. You're driving the ammonia and nitrate concentrations down to new lows. Some additional benefits to operating this kind of system and in the way that we've set it up. There's been a lot of work done over 20 years now, with our process and our instrumentation and controls team, to with this technology, to try to minimize and still be very functional how much new instrumentation is needed. Some of these facilities you might go into have multiple trains, especially larger facilities, and more often than not, although understand it's never perfect, but usually there's a fairly equal parallel split of flows and loads, and for the most part the same equipment in the different trains. That affords an opportunity to be able to outfit, say, one master train with all of the instrumentation you want, but then use that some of that information and have just, say, one ammonia probe in parallel trains, and be able to use the information from the master train as inputs to the algorithm that's controlling the other train that has a minimum amount of instrumentation. So that's a cost-saving measure to try to keep the initial investment down from an instrumentation standpoint, and also the maintenance costs. A lot of this instrumentation, you do have to be pretty careful and take very good care of it for it to work well. Certainly, the overall system will be better optimized if you have all of the instrumentation and all of the trains. But it's not much of a drop-off with the work that we've put in to really fine-tune how this master-slave dynamic works for the system. In aeration systems where there are separate aeration zones within a single train, there is dynamic air distribution control to add that additional level of fine-tuning into the control of the system, where in general the upstream tank is going to have the higher DO and smaller DO as you move downstream, and really throughout the profile of that reactor in how those different zones are controlled, really optimize the optimization there, or optimize the system there. If there are more than two controllable zones, that is a condition that is particularly well suited to incorporate some additional BioP into the system. Even if you have a system that's not designed to do biological phosphorus removal, the algorithm that we're working with here has sort of tack-on features to make BioP even more, allow you to realize BioP in systems where you don't, where you hadn't necessarily really designed for it. And that's another of the additional benefits. You see N2O minimization at the top. That is one that's been done in the past. We don't see a whole lot of application for that, but it is available if you had a application where you really wanted to target greenhouse gas emissions and keep N2O concentrations being released. There is a variant of the DON algorithm that also incorporates monitoring the N2O being released and will balance everything associated with the nitrogen in that plant, considering ammonium nitrate and the N2O. There is a BioP safe, which is a when you have an effluent phosphorus limitation, the control with the DO and N feature, if it's really, really well optimized, there are times where you can get into conditions where you might get some anaerobic conditions toward the tail end of the system. And if that happens, you can release some phosphorus from the biomass. If you're familiar with biological phosphorus removal, as I'm sure a lot of you are, you're very well aware of that type of reactor condition leading to a release of phosphorus. So there's a feature that goes along where we will ensure by monitoring phosphate that doesn't happen. And so that adds another layer to ensure compliance with any phosphorus limits. And then I also talked a little bit already about the BioP removal feature. The DO&N control is well suited to allow facilities, because it's a continuous monitoring of both ammonia and nitrate, and controlling aerobic and anoxic events. There is also a RAS control feature and an internal mixed liquor recycle control feature. And those can be controlled in conjunction with the DONN feature to implement anaerobic conditions when we have a carbon source coming into the plant and we have overall lower load conditions and we know we don't need to use the entirety of our volume to nitrify and denitrify. We can, say you're thinking, times overnight, any times that your plant isn't fully loaded, the more often that you could incorporate those kind of conditions, those anaerobic conditions into the process train, the more BioP bacteria you're going to be able to grow and keep in that reactor system. So we've seen this work very well in a number of our facilities where you have a facility that isn't designed to do biological phosphorus removal at all, and through the smart BioP feature is able to get pretty significant BioP and reduce your coagulant consumption and save some operating costs there. So a couple of profiles on some real world successes that we've seen with the Hubgrade Performance Plant, and specifically the DO and nitrogen feature. A relatively small facility here in Denmark. This is a facility that actually was going to be taking on some additional industrial flow from a potato industry, and was stuck with a choice between adding additional aeration tank volume or trying to optimize what they had with the Hubgrade Performance Plant system. They chose the latter, were able to achieve a 35% increase in capacity that they needed, and in doing so, improved their total nitrogen in their effluent by 20%. Incorporated the DO and nitrogen feature along with 4 other features at the facility. And as I said, the more of those features that you tack on the secondary system, the more they really work in conjunction to fully optimize the control of the facility. I noted at the beginning that these features are applicable in industrial situations. Anything that has an aerated tank that has a need to nitrify and or denitrify can derive benefit from these sorts of enhanced methods of control. So here's a particular industry that needed to comply with more strict effluent total nitrogen requirements. They made some process changes, implemented at the time Aquavista plant. I noted the brand name change before, and really cut their total nitrogen limit, or total nitrogen effluent, by 50% to allow them to stay in compliance with that stricter effluent total nitrogen, and to be able to meet that new stricter total nitrogen limit without having to add additional volume into the system. So one last look at a success story. This is probably our most prominent installation. It is in Denmark. That is a wastewater utility that has 4 wastewater treatment plants in that area that the utility manages. They have implemented a number of different features. They have been an excellent partner in working with us to help advance newer features. A lot of the work that we're doing with collection system optimization and using weather APIs and real-time fluctuating power prices to tie into how the collection system is controlled. They've been a great partner in advancing these advanced model-based control techniques there. But they've also, for many, many years, operated with the DONN and other features and seen very significant savings in terms of energy, chemical consumption, and have been very consistent performers in producing a low effluent total nitrogen from the treatment facilities. So in summary, we've seen that, automated control in our aeration systems, particularly when we're doing nutrient removal, they have, evolved over time. A lot of systems out there today are still, operating okay with just DO control. There are many systems out there that are using ammonia-based aeration control, and there are lots of different feedback, feed forward, combination of the two, et cetera, ways to incorporate that. And you reach a higher level of control when you incorporate things like solids retention time control and other things that are focused on controlling the biomass and the quality and condition of the mixed liquor itself. We believe Hubgrade Performance Plant really takes things to the next level. It's really the next evolution of control in our nutrient removal systems, with utilizing digital twin technology and utilizing multi-criteria based control with ammonia and nitrate monitoring, and leading to the ability to, in real time, determine new DO settings and manage the top level reactor environment between aerobic and anoxic conditions, and keep that optimized throughout the day, every day, 24/7, 365. And we've seen, we've been employing this system for a number of years in many plants, and have seen very well established results with averages of 20 to 50% improvement in effluent total nitrogen from these facilities, and 10 to 30% reduction in aeration energy, and have seen improvements and increases in capacity as well that help avoid additional capital expenditure and really make the best use of infrastructure on hand. So with that, I have concluded my portion here of my pre-made slides. So I am going to open it up here and ask Jill if we have any questions.
Yeah, thank you very much for that, Mark. Very informative presentation there. We do have some questions that came in, and just to remind everybody as well, if you have any questions, feel free to type those over in the questions panel. And we will try to, we've got a few minutes left here, so we'll try to get through as many of these as we can, but if we don't get through all of your questions and don't answer yours, we will follow back up with you individually. So with that, Mark, I do have one that's here. How many DO and ammonium probes are needed in a reactor volume of, say, roughly 2.5 million gallons?
So in a reactor that is 2.5 million gallons, it's tough to pick, say you would need 1 or 2 or 3 without really knowing how that reactor is, how well it's mixed. Is it pretty long and skinny with that really sort of functions as more of a plug flow reactor? Does it have a couple of zones? The best way I can answer that is to say, in most cases, we would seek to keep the instrumentation to a minimum and say have 1 ammonia analyzer and 1 nitrate analyzer, and maybe we have a couple of DO probes, but it could be a necessity to really optimize things to have that broken up into different zones. So it really depends a lot on the configuration and the mixing.
Great, thank you. Another question that came in is, to achieve process control in a more general sense, based on real-time monitoring of ammonia concentrations, do you have any preference regarding what type of instrumentation to use? For example, wet chemistry type of analyzer with lower detection limit and longer sampling interval, or ammonia electrode with higher detection limit and more frequent sampling?
Yeah, that's a good question, and one that we certainly have to pay attention to. We are generally more fond of wet chemistry analyzers, and the reason being, in a well-operated, fine-tuned system, the ammonia and nitrate concentrations where you are measuring them in the reactor are typically going to be very low. And you need to have, good precision at those low levels. An ISE probe just isn't going to do it. Now, if you have a system where you're just more focused on maintaining compliance and you're not, looking to say have your total nitrogen level, down at an absolute minimum, maybe you can get by okay. It won't be optimized as much as it should. But we definitely prefer the wet chemistry analyzers. On the nitrate, a UV probe is generally okay, but we don't recommend the use of ISE probes. And recognizing that we do have different sample times, really there isn't much sacrifice there. We have these systems utilizing, say, a single ASA ChemScan 4100 with where we're using that single unit to do ammonia, nitrate, and phosphate. And so with that, we don't get phosphate readings really often. If I remember correctly, it's maybe every 10 minutes. But it's adequate for the system to work well.
Great. I think we've got time for maybe one or two more quick questions. Does Veolia provide its own sensors for use in this control system?
So we are not a instrumentation manufacturer. When we implement any of our systems, whether we're doing a new ANITAMOX system at a treatment facility, or we're doing a major control upgrade with Hubgrade Performance Plant, or whatever it is we're doing, we oftentimes do provide the instrumentation. But we are not, and that's for more of a sole source responsibility. Try to avoid, if something isn't going quite right, finger pointing down the line. But specific to Hubgrade Performance Plant, there are just as many times where the owner procures all the instrumentation entirely on their own, and we don't touch it. It is not a requirement that we provide it. And we, outside of the functional aspects and ensuring we have the proper measuring range and proper precision within that range, we are not, we don't adhere to any particular manufacturer. So if it's a YSI, if it's a HOC, if it's an ASA ChemScan, et cetera, yeah, as long as it is suitable to do the job. If as an owner, if the plant staff has a preference, if they like one thing over another, that is something we will work with. No problem there.
Great, thanks, Mark. I think we are just a little bit actually over time. So with that, we'll conclude our webinar today. We do very much appreciate all of your time spending with us today. One thing I forgot to mention at the beginning, this presentation has been recorded, so you will receive a copy of this in the next day or two. And then we also do invite you to please take that survey as soon as we conclude this. That would be greatly appreciated. And if you enjoyed today's Tech Talk, please feel free to go over to our website, again, www.veoliawatertech.com, to check out some of the upcoming Tech Talk series. So with that, that concludes our webinar today, and we very much appreciate your time. Thank you.